Hey guys, this is test 45 game 3. This is the photographs game. It's an in-out game, also known as selection. We know this because we want to see which of the friends appear in a photograph together, and the rules are actually all conditional, even though it might not appear to be the case at first glance. We've got lots of conditional indicators here. We've got the word every appearing in the first, second, and third rules, and then we have the word any appearing in the fourth rule. And the words every and any are sufficient condition indicators. So whatever immediately follows those words is going to be the sufficient condition of a conditional statement and will appear prior to the arrow. So the first rule here tells us that if we have S, then we will have W. Now I know that it has W first in the sentence, but that is actually irrelevant because the presentation of the order of conditional statements does not ultimately matter. What really matters is the conditional indicators. So the first rule, W appears whenever S appears, should really be S arrow W. Now the contrapositive of the statement, we should immediately take it and then take the next rule that we can link to it. So S arrow W, contrapositive not W, then not S. Now the next rule says that S appears every time that U appears, which really means U arrow S. So contrapositive not S, then not U. Now the next rule mentions the variables R and Y, which we did not previously see in our rules. So I'm going to skip that rule for now and come back to it when we have new information that will allow us to more easily link that to what we already have ideally. So the final rule here says neither T nor R happens when W happens. So W then is requiring not T and not R. So W arrow not T and W arrow not R. Contrapositive, if we have either T or R, then we will not have W. So I link those to the front of the bottom chain. Now the final rule, the rule that we skipped, says R happens when Y does not, meaning not Y leads to R. We already have R over here, so I can just stick not Y in front of it, leading to positive R. Then the contrapositive of that would be not R leads to Y. So this is every rule and its contrapositive linked together to form long conditional chains, and this is our initial setup for the game. So question number 13 is a typical orientation question, simply asking us for a valid scenario of people that we could have in at the same time. So I'd recommend taking one ruler inference, applying it to all 5 choices, looking for violations. So here we can take the information, for example, that whenever we have U, we will have S, W, and Y. We also know that U would require T and R out, but let's try to think about one thing at a time, one thing that we can easily hold in our head. So whenever you have U, you have to have S, W, and Y in. So any choice mentioning U must have those 3 other things. Choice D mentions U, yet mentions S and Y, but not W. So D is bad for that reason and is eliminated. Choice E mentions U, mentions S, but does not mention either W or Y, so E can be eliminated for that reason. We've exhausted the usefulness of this because none of the other choices mention U, so we'll skip that for now. Move on to the next thing. Whenever we have S, we have to have both W and Y. So any choice mentioning S must also mention those 2 other things. Choice A mentions S, has W, yet does not have Y, so A is eliminated. Neither B nor C has S, so we'll skip that for now. Having W requires having Y, but choice C complies with that issue, so we're good for that. We're just down to 2 choices now. So now I'd recommend taking the bottom chain and saying, okay, whenever we have T, we have to lack W, S, and U. Same goes for R, but I'll start with T. Whenever we have T, we lack W, S, and U. Choice B mentions T, yet does not mention any of W, S, and U, so it's okay on that issue. Choice C does not mention T, but now I'm going to use the fact that R requires W, S, and U to be out, and choice C has R yet also has W, unacceptable, so for that reason C is eliminated and B is our answer to number 13. Next, number 14, if we have T and Z in, what must be true? So T in requires W, S, and U out. Z is not affected. Z is essentially a random variable in this game. I'm getting no rules about it. I'm going to make a little in-out table right here for number 14. Little T diagram, in and out. So we have T and Z in, and we know that when those guys are in, W, S, and U will have to be out. Now Y and R are not affected by this. They're essentially on the fence. But because whenever Y is out, R is in, and whenever R is out, then Y is in, we know that we always have to have at least one of those two guys in. So I'm going to put Y/R in the in column and leave the other one of those two R/Y on the fence. So going forward, let's just run through the choices. These guys essentially aren't even that important because this question is a must question. So they're more likely to ask about W, S, and U, not about Y and R. Anyway, let's run through the choices. Must we have S in? No, in fact, S has to be out, so A is gone. Must we have Y in? No, Y could actually go either way, right? No rules regarding its placement. So B is gone. Must we have W? No, W has to be out, so C is gone. D, R does not appear. R's placement is undetermined. We don't know whether it's in or out, so D is gone. And then E by elimination, of course, U does not appear. We have that as a given from the very beginning. So if you wanted to, you could have scanned through the out column looking for the choices saying that one of those three guys must be out. I simply went through all 5 choices for purposes of being complete. So E is our answer, number 14. Next, number 15. If Y was out, then what's the maximum number of people we could have in? So I'm going to make a little in-out table for number 15, putting Y out and seeing what happens as a result. So if Y is out, R has to be in, and if R is in, W, S, and U all have to be out. So we're really losing a lot of people here. So who could we potentially have in? We could have T, and we could have Z. The other guys are all determined. So I'm going to, in order to be complete here, now I'm going to put T and Z on the fence because their placement is not actually known. But because they're asking us for the maximum number of people in, we're going to want to put T and Z who are on the fence. We're going to want to put them specifically in the in column. So our maximum would be 3, R, T, and Z. So choice D says 3, so D is our answer to number 15. Next, number 16, if U and Z appear together, who else must also appear? And we're talking about in, of course. So I'm going to make another little in-out table for number 16. I'm going to put U and Z in, and we know that when we have U and Z, we're going to have S, W, and Y as well due to the top chain. U requires S, W, and Y to be in. So those guys are going to go in as well. So S, W, and Y are in. And we know, of course, that U in forces T out and R out indirectly. So those guys are going to be in the out column. And this accounts for everybody. So they're asking us how many other friends must also appear. The word also is very important here. Our total number in, as a must, would be 5. But those also, meaning in addition to U and Z, is only 3 people, S, W, Y. So the actual answer to this question is B, 3, not the number 5. If they wanted to be really nasty, they could have made the number 5 as an answer choice, but perhaps it's even worse of them not to include 5 as a choice because now you just kind of get confused if you thought that 5 was the correct answer. It is actually 3 because U and Z should not be included in our count. So that's number 16. Next, number 17. If we have exactly 3 friends together in a photograph, each of the following could be true except, so what cannot be true if we're going to have 3 people? Now perhaps we could have made use of some of our previous in-out tables. You can feel free to do that in the hopes of possibly eliminating some of the choices here. But I'm just going to run through the choices as listed. So choice A, could we have both S and Z appear in? So if S was in, we would have to have W and Y in as well. So any choice mentioning S in is going to also have W and Y in. So if I'm just going to make a little in-out table here really quick. If S was in, and Z was in, and S in requires W in and Y in as well, that's already 4 people in the in column. And they said if exactly 3 friends appear. So you got to remember that S in is requiring W and Y as well. So if you bring in Z, you're already reaching 4 people, and they said 3. So A is actually our cannot, and as such is our answer to number 17. I'll talk briefly about the other choices though. So could we have both T and Y? Well, T in just requires W, S, and U out. No reason we couldn't have Y in as well, and then have somebody like R or somebody like Z. That'd be fine. So either way, we could reach 3. And B is eliminated because it's a could. Looking at C now, W and S both appear. W and S in just requires Y, and those guys, S, W, and Y, could be our 3. That would work because no one else would need to be in as well. C is gone. D, Y, and Z both appear. Y in doesn't require anybody else, and Z is a variable about which there are no rules at all. So that's only 2 people in. We could take in a third as well. It could be W, it could be R, it could be T. Any of those people could be the third. So D is gone. And then E, Z and R both appear. R in simply requires W, S, and U to be out, so it's not requiring anyone else in. So we could have R and Z as 2 people, then have a third like T or like Y. That would be fine. So E is a could as well and is gone, leaving A as our answer to number 17.